Okay, so today our first goal will be to prove an important theorem due to Banach, Aloglu, and Bourbaki. So we start with the following definition. Suppose that x and y are topological vector spaces, and suppose that M is a family of continuous linear operators from x to y. And we say that M is equicontinuous if for each neighborhood of 0, v y, there is a neighborhood of 0 in x, a neighborhood u of 0 in x, such that each operator from M takes u to v. T of u is contained in V. In Russian, equicontinuous is равностепенно непрерывно. So if we write this condition for a single operator T, then this condition means just that T is continuous at 0, or equivalently continuous. But here the point is that we have a family of operators, and this neighborhood U doesn't depend on T. That's the reason why such families are called equicontinuous. Here is a useful special case, an example and exercise at the same time. Suppose that x and y are normed spaces. In this case, our family M is equicontinuous, even only if it is bounded. M is bounded with respect to the usual operator norm on this space. Okay, so let's also adopt the following convention. Some time ago, we introduced dual pairs and weak topologies. In particular, we discussed the weak star topology on the dual of any Hausdorff locally convex space. So actually, we can define the weak star topology on the dual of any topological vector space. And the definition is absolutely the same. So if X is a topological vector space, then we define the weak star topology, on the dual, to be the locally convex topology generated by the following family of seminorms. So the seminorms are indexed by elements in X, and such seminorm is given by the following formula. So in other words, the definition of the weak star topology of the dual is exactly the same as in the case of Hausdorff locally convex spaces. The only difference is that in the general case, X and X star don't form a dual pair. But nevertheless, we can define the weak star topology exactly as in the locally convex case. Okay, now we have the following fundamental result. Theorem which is usually referred to as the Banach-Aloglu-Bourbaki theorem. Russian language literature, the standard name is the Banach-Hologlu theorem. In the English language literature, the standard name is the Alaoglu-Bourbaki theorem, or just the Alaoglu theorem. But in fact, this theorem is due to many people. I'll tell you more about history a bit later. So suppose that X is a topological vector space, and suppose that M is an equicontinuous subset of the dual. Then M is relatively weakly star compact. That is, its closure in X star is weakly star compact. It's compact with respect to the weak star topology. The proof is a nice application of Tikhonov's theorem about products of compact spaces. So first of all, we embed X into the space k to the power x, which consists of all k-valued functions on X. As usual, K is our base field, either the field of real numbers or the field of complex numbers. And let's observe that the weak star topology on X star is nothing but the induced topology. The topology induced from the product topology on k to the power x. On k to the power x. This easily follows from the definition of the weak star topology. If you write explicitly the standard subbase of the weak star topology, then you will easily see that this is nothing but this subbase consists of intersections of the standard subbase of the product topology with this space of continuous linear functionals. Okay, why is it useful? So let M bar denote the closure of M, but we take the closure not in X star, but in k to the power x. And to prove our theorem, we need to prove two things. So we want to show that first of all, M bar is compact, and second, we will prove that M bar is actually contained in X star. So these two statements will imply that M is a relatively weak star compact in X star. Okay, so first of all, let's show that M bar is compact. Let's write explicitly the condition that M is equicontinuous. So by the equicontinuity of M, there exists a neighborhood of 0. There exists a neighborhood U of 0 in X, such that for each functional f in M, we have the following inequality. The absolute value of f of u is less than or equal to 1 for each little u in our neighborhood. Okay, let's now consider the projections of M. So M sits in k to the power x. So we can consider the projections of M on each copy of the field k in this product. So for each x in X, let Mx be the following subset of k. it consists of all elements of f of x, where f runs over M. I claim that this set is bounded in K. Well, why is it bounded? Indeed, if you take an arbitrary element x in our space big X, we can always find a positive number lambda such that lambda x sits in U. This follows from the continuity of the multiplication. So we fix x, so when we consider lambda x goes to 0 as lambda goes to 0. So if lambda is small enough, this will be in our neighborhood U. Okay, but well, we substitute this vector to f, and we conclude that f of lambda x is less than or equal to 1, or equivalently f of x is less than or equal to 1 over lambda for each f in M. And so this implies that Mx is bounded. Mx is bounded. Okay, so now we take our M, and we observe that M is obviously contained in the product of its projections, Mx. So this is clear, and when we take closures, we get such an inclusion. And this is the place where we apply Tikhonov's theorem. Well, indeed, this space here is compact by Tikhonov's theorem. So M bar is a closed subset of a compact space, so it is itself compact. M bar is compact. Okay, so this proves our first claim. And now we want to show that M bar is contained in X star. Okay, we take any two elements x and y in our space, and alpha and beta in K, and observe that the following map, a map which takes f to f of alpha x plus beta y minus alpha f of x minus beta f of y. This is a map from K to the, because M consists of linear functionals. Okay, this implies that it vanishes on the closure of M. It vanishes on the closure of M, on M bar, closure of M in K to the power X, but this means exactly that M bar consists of linear functionals. So M bar is contained in the algebraic dual of X. Let's recall that X hash is our notation for the algebraic dual. That is the space of all linear functionals on X. Well, this is not the end of the story, because we still have to show that M bar is contained in X star. That is, functionals from M bar are continuous. But this is also rather easy. Let's look at the following set. The set of all f in K to the power x, such that for each element little u in our neighborhood U, we have the following inequality. So what can you say about this set? The set is clearly closed in K to the power x. Again, this follows from the definition of the product topology. Also, if we look here, we see that this set contains M. and contains M. So it contains M bar. It contains the closure of M. So we see now that this inequality holds for each f in M bar. And now, if you take an arbitrary positive epsilon and an arbitrary vector, say v, in epsilon u is also a neighborhood of 0. And by linearity, we see that for each f in M, we have f of v is less than or equal to epsilon. So f is continuous at 0, that is, it is continuous. And we conclude that M bar is actually contained in X star. That is, all functionals in M bar are continuous. And this completes the proof. Okay. Our next result is a refinement of the Banach-Bourbaki theorem for separable spaces. We'll suppose that X is a separable topological vector space. And suppose that M is an equicontinuous subset of the dual. I claim that M is relatively weakly star compact and weakly star neutralizable. It's not only relatively weakly star compact, but it is also weakly star neutralizable. Here is a sketch of proof. So I will leave some details as exercise for you. But the idea is the following. So we choose a countable dense subset in X. So let Xm be a countable dense subset of X. And let's introduce the following countable family of seminars. So the seminars will be indexed by natural numbers. And the nth seminar is defined as follows. So this is the absolute value of f at xn. We have the following exercise. First of all, the topology generated by this family is metrizable. This exercise is already contained in our exercise sheet 3. More generally, the exercise is that local and convex topology is metrizable if and only if it can be determined by countably many seminars. And the second part of the exercise is the following. This topology, tau of P, and the weak star topology induce the same topology on M. I don't claim that they are the same everywhere. But after we restrict these topologies to M, they will be the same. On the whole space, the weak star topology is usually stronger than tau of P. Well, modulo these exercises, this is the end of the proof, because part 2 and part 1 imply that M is weakly star neutralizable, and our previous theorem shows that M is relatively weakly star compact. In particular, we have the following corollary for normed spaces. Suppose that X is a normed space. Then, first of all, the closed unit ball in the dual space X star is weakly star compact. This is a special case of our previous theorem because it is obviously equicontinuous. So it is a weakly star compact. Second, if X is separable, then the ball, called unit ball in X star, is weakly star compact and weakly star neutralizable. And finally, part 3 is in fact an equivalent form of part 2. So I'll write it down explicitly because this is the original form of our theorem due to Banach. It was proved in 1929. If X is separable, then the closed unit ball X star is weakly star sequentially compact. Or maybe it's better to say sequentially weakly star compact. I don't know what is better, sequentially weakly star compact or weakly star sequentially compact. But it's clear what I mean. It is a sequentially weakly star compact. This means that each sequence in this ball has a weakly star convergent subsequence. Or equivalently, every norm-bounded sequence in X star has a subsequence which converges with respect to the weak star topology. So this is the original form of the theorem proved by Banach in 1929. The point is that this theorem was proved about the same time where Alexandrov and Orson introduced the general notion of compact topological space. So this notion was not so popular in those times, and so Banach formulated the sequential form of this theorem. And the proof was different because Tikhonov's theorem was not available at those times. At the end of the 1930s, several people independently observed that, in fact, this result easily follows from Tikhonov's theorem. So essentially, the same result was obtained independently by Orloglu, Bourbaki, Shmulyan, and Kakutani. By the way, Bourbaki, in this context, Bourbaki means Dieudonné and Schwarz. Because of the whole Bourbaki group, only Dieudonné and Schwarz, and later Grothendieck, work with topological vector spaces. Okay, so this is a very useful result. By the way, it's useful to compare this result with the fact that this ball is never compact under the norm topology if X is infinite dimensional. But it is a weakly star compact. Okay, that's all I wanted to tell you about topological vector spaces. So our goal for the rest of the course is first to discuss the basics of commutative Banach algebras, and then to apply this theory to the study of spectral theory for bounded normal operators on a Hilbert space. So our final goal in this course will be to prove the spectral theorem for bounded normal operators on a Hilbert space. And on our way, there is another very important result, namely the Gelfand-Dynamic theorem on commutative C-star algebras. Okay, so the basic notions of the theory of commutative Banach algebras are the maximal spectrum, and the Gelfand transform. From now on, we will look only over the field of complex numbers. So this will be our basic convention. Everything will be over the complex numbers. As usual, by an algebra, I always mean an associative algebra over the complex numbers. And we say that if you have an algebra, and we say that our algebra A is unital, even has an identity element. It has an identity element, which will be denoted like this. If A is unital, then we can consider the so-called multiplicative group, that is the set of all invertibles in A, which will be denoted by A cross. It is the set of all invertible elements. Okay, so let's now suppose that A is a commutative unital algebra. A commutative unital algebra. And let's recall the following algebraic definition. Suppose that we have a proper ideal, I and A. A proper ideal that is an ideal different from A. A proper ideal I is maximal. Is maximal if it is not strictly contained in any bigger proper ideal. If there is no proper ideal I, or another ideal J, such that J is strictly bigger than I, and J is proper. In other words, a maximal ideal is a maximal element in the ordered set of all proper ideals of A. Sometimes it is convenient to characterize maximal ideals in slightly different terms. Here is a useful exercise for you. A proper ideal I is maximal even only if the quotient of A modulo I is a field. A standard algebraic exercise. We now introduce the maximal spectrum of A. So by definition, the maximal spectrum of A is the set of all maximal ideals, which will be denoted like this. The set of all maximal ideals of A. Here's a basic example and an exercise at the same time. So what can we say about maximal ideals of the polynomial algebra of one variable? Well, it's rather easy to show that there is a one-to-one correspondence between the maximal spectrum of the polynomial algebra and the complex plane. More exactly, if P is a point on the complex plane, then the corresponding maximal ideal, as denoted by MP, consists of those polynomials which vanish at P. So this is a bijection between the maximal spectrum of the polynomial algebra and a complex plane. In fact, this result extends to polynomial algebras of several variables, but this is not so easy. And in fact, this is a weak form of the famous Hilbert's Nullstellensatz. Bijection, a bijection. A one-to-one correspondence, I mean a bijection. So this correspondence, which takes each point P in here to this maximal ideal, is a bijection between the complex plane and the maximal spectrum of the algebra, of the polynomial algebra. Okay. How about the existence of maximal ideals in the general case? Well, they always exist, and moreover have the following result, following proposition. Each proper ideal of A is contained in a maximal ideal. The proof is a standard application of Zorn's lemma. So we start with a proper ideal, I, and we introduce the following set, that's denoted by M, the set of all proper ideals, J, which contain I. So clearly it is not empty because it contains I as well. It is a partially ordered set by inclusion. It's a Poe set, a partially ordered set. And I claim that the set satisfies the conditions of Zorn's lemma. Well, why is it so? So we should take an arbitrary chain in M. So indeed, let C be a chain in M. And we want to show that C has an upper bound in M. Let's take that the union. Let K denote the union of all ideals in C. Clearly K is an ideal. Because C is a chain. So the union of any chain of ideals is an ideal. And clearly it contains I. We have to show that it's a proper ideal. So why is it proper? Well, each ideal J is proper, so the identity of the algebra is not contained in J, or each J in C. Here I use the simple standard fact that an ideal of a unital algebra is proper if and only if it doesn't contain the identity of the algebra. So the identity is not in any ideal in C, and so it is not in K. But this implies that K is proper. In other words, K is an element of our set M, and clearly K is an upper bound for C. That is, it is bigger than any ideal in C. So we see that the conditions of Zorn's lemma are satisfied. So every chain has an upper bound. And so by Zorn's lemma, M has a maximal element. And this element will be a maximal ideal which contains I. And this completes the proof. Okay. Let's now introduce another set which is closely related to the maximal spectrum. First of all, we recall the following definition. By definition, a character of A, a character of A is an algebra homomorphism from A to the complex numbers. And let's observe the following. Let's observe that if A is unital, and here we assume that A is unital, and chi is a non-zero character, then chi is also unital. So it takes the identity of the algebra to the identity in the complex field. Why is it so? Well, it is non-zero, so in particular it is a linear functional, so its image is a vector subspace of the one-dimensional space, so it is surjective. And it's a simple algebraic exercise to show that if we have a surjective homomorphism between unital algebras, then it always takes the identity to the identity. Okay. So now we introduce the following set. We define the character space. The character space of A to be the set of all non-zero characters. And we denote this set by A hat. Set of all non-zero characters, or equivalent to the set of all unital characters. There is an obvious relation between this set and the maximal spectrum. So let's observe that for each character, for each non-zero character of A, its kernel is a maximal ideal. This is clear because it's an ideal, because chi is an algebra homomorphism, and it is maximal because it has codimension 1 in B. So we have a map from the character space to the maximal spectrum, which takes each character to its kernel. It's easy to show that this map is always injective. So we have the following proposition. The map from A hat to the maximal spectrum, which takes each character to its kernel, is injective. Well, this is very easy. You have two characters, chi1 and chi2, such that the kernels are the same. So in particular, they are linear functionals. And it's standard factor in linear algebra that you have two linear functionals with the same kernel, then they are proportional. So there is a number, lambda, such that. And to show that lambda is 1, we simply evaluate these characters, these two functionals on the identity. So each of them is unital. So we have this. So this is lambda chi2 of 1, but chi2 is also unital, and so this is equal to lambda. So in other words, lambda is 1, and so chi1 equals chi2. And this means that our map from here to here is injective. Now, an actual question is it bijective? Well, an answer depends on the algebra. Here's a couple of examples. Examples and exercises. First of all, you could take, for example, the polynomial algebra in one variable. Then this map is bijective. Yeah, it's a field, but not necessarily a field of complex numbers. That's the point. But for the polynomial algebra of odd variables, this is true. It's indeed a bijection, and in fact, this result extends to an arbitrary, finitely generated commutative algebra, in particular to the polynomial algebra of several variables. But in the general case, this is not true. For example, let's suppose that A is a field which properly contains a field of complex numbers. For example, we can take the field of rational functions in one variable. In this case, the character space is empty. This is an exercise. There are no characters on a field which is strictly bigger than the field of complex numbers. But the maximal spectrum is non-empty for the simple reason that the zero ideal is maximal, and in fact there are no other maximal ideals. So the maximal ideal, the maximal spectrum consists of a single point, the zero ideal. So in this case, this map is not a bijection. So our next goal will be to show that this map is a bijection, provided that A is commutative unital Banach algebra. So now we come back again from algebra to functional analysis. First of all, we'll prove the following lemma. Suppose that A is a commutative unital Banach algebra. Then each maximal ideal of A is closed. Well, why is it so? Why is it closed? Let's take maximal ideal. Let I be maximal ideal. And let's take the closure. So suppose that I is not closed. Suppose that I is not closed. Is not closed. So what can I say about the closure? Well, the closure of an ideal is easily seen to be an ideal. The closure of an ideal is an ideal. But I is maximal. And this implies that this closure is equal to A by maximality. Well, what can we say about I? Equivalently, this means that I is dense. I is dense in A. And let's now recall a standard fact from Banach algebra theory. The fact is that the set of invertibles, the multiplicative group, is always open in A. So it is open, and so the intersection of I with this set, with the set of invertibles, is non-empty. This is non-empty because the set of invertibles is open. Well, this means that I contains an invertible element, but this can happen only if I equals A. I equals A, and this is a contradiction. Because I was assumed to be maximal ideal, and the maximal ideal is proper by definition. Well, the contradiction shows that I is actually closed in A. It is closed. Well, as a corollary, we see that a commutative unit of Banach algebra doesn't have dense proper ideals. Because each proper ideal is contained in a maximal ideal, and by the previous result, maximal ideal is closed. So an arbitrary ideal is never dense in A. Okay, now we come back to this map, and we prove that it is bijective, provided that A is a commutative unit of Banach algebra. If A is a commutative unit of Banach algebra, then our map from the character space to the maximal spectrum is bijective. Well, we already know that it is injective. So now we have to show that each maximal ideal is a kernel of a character. Okay, so let's take a maximal ideal. Let's take a maximal ideal I. By the previous lemma, I is closed. I is closed in A. So let's now take the quotient of A modulo I. Well, the quotient of a Banach algebra modulo a closed ideal is a Banach algebra. But the ideal is maximal. And so the quotient will be Banach field. A modulo I is Banach field. And now we recall the Gelfand-Mazur theorem, which states that each Banach division algebra, in particular each Banach field, is isomorphic to the field of complex numbers. So by the Gelfand-Mazur theorem, we conclude that this quotient is isomorphic to the complex numbers. And now to complete the proof, we just consider the following picture. So we have the quotient map of A on the quotient. This quotient is isomorphic to the complex numbers. So the composition of the quotient map and of this isomorphism is a character, chi. Chi is a character. And by construction, I equals the kernel of chi. And that's it. So this implies that our map is surjective. And so it is bijective. As a corollary, we get the following useful invertibility criterion for elements in our algebra. So as before, we suppose that A is a commutative unital Banach algebra. And I claim that an element in our algebra is invertible. Even if characters, non-zero characters, don't vanish on A. For each chi of A is not zero. Well, the left-right implication is clear. Because a non-zero character is a unital homomorphism, and we know that a unital homomorphism always takes invertibles to invertibles. And to prove the right to left implication, we do the following. We take an element A and A, and we suppose that A is not invertible. Suppose that A is not invertible. Then we can consider the principal ideal generated by A. And the principal ideal generated by A is a proper ideal. Each proper ideal is contained in the maximal ideal. It's contained in the maximal ideal I. But we already know that I is a kernel of a character. And that's it. So this implies that chi vanishes at little a. Okay, so from now on, let's adopt the following useful convention. We'll often identify the maximal spectrum with the character space. Sometimes it is more convenient to think of elements of the set as characters, and sometimes in other situations it is more convenient to interpret them as maximal ideals. But anyway, there is a standard bijection between this set, so we will identify them by means of this standard bijection. Okay, so far, the set, the spectrum, or equivalent to the character space, is just a set. our next goal is to topologize this space. So as before, we assume that A is a commutative unital Banach algebra. And let's recall that each character of A is automatically continuous and is contained in the unit ball of the dual. That is, the norm of each character is less than or equal to 1. So we have the following conclusion. So B is as usual the unit ball. So now we introduce a topology on the character space, or equivalently on the maximal spectrum. So by definition, the Gelfand topology on the maximal spectrum, or equivalently on the character space, is the topology induced from the weak star topology. Is the restriction of the weak star topology on A star. So A hat and so the maximal spectrum are they are the same actually. So they become topological spaces. What can I say about the space? I claim that the space is always compact and Hausdorff. The maximal spectrum is compact and Hausdorff. Well, why is it Hausdorff? Well, this one is clear because we know that the weak star topology is always Hausdorff. A star equipped with the weak star topology is Hausdorff. And hence, so is the maximal spectrum. Why is it compact? To prove that this set is compact, we use the Banach-Huber theorem. Well, indeed, the unit ball of the dual space is weakly star compact. And this is a subset in the unit ball. So to prove the compactness, it's enough to show that this set is closed. So to complete the proof, to prove that it is compact, it suffices to show that it is closed. And A hat is closed in the unit ball with respect to the weak star topology. So this follows from the Banach-Huber theorem. Well, why is it closed? This is also rather easy, because if you take two elements, little a and little b, in A, we can consider the following map, the map from the unit ball, equipped with the weak star topology, to the complex numbers, which takes chi to chi of A, B. Well, since it is defined on all functionals, it's better to use another letter, for example, little f. So it takes each f to f of A, B minus f of A, f of B. And this map is continuous, because indeed, again, it's a combination of three. So this is a product of two evaluation maps. This is an evaluation map, and the product and the difference of two continuous maps are continuous. So this map is continuous. And another map, well, we'll actually need two maps. The second map is just the evaluation of the identity. And they are continuous for the weak star topology. Well, so they are continuous, and to complete the proof, we just observe then that A hat consists of precisely those functionals for which this is 0 and this is 0. So it follows from this equality and from the continuity of these two maps that A hat is closed. A hat is closed in the unit ball. Okay, so the maximal spectrum is a compact Hausdorff topological space. No. F where? Oh, of course. F of 1 minus 1. Okay. Okay, so now we are ready to introduce the Eagle-Fund transform. We define the Eagle-Fund transform. Eagle-Fund transform of an element Lilly in our algebra to be the following function: A hat defined on the maximal spectrum by the following formula. So we interpret each point in the space as a character, and we define A hat by this simple formula. This looks like something trivial, but the truth is that trivial definitions are often very useful. So what can I say about this function? First of all, I claim that this function is continuous. This function is continuous on the maximal spectrum. To prove the continuity, we consider the canonical embedding. Let little I denote the canonical embedding of A into the bidual. The canonical embedding. And we observe that after we look at this definition, we observe that A hat is nothing but the restriction of I of A to the character space, just by definition, by construction. And to complete the proof, we recall that the image of the canonical embedding consists precisely of those functionals on a star, which are weakly star continuous. In particular, I of A is weakly star continuous. So the Gelfand transform of each element in our algebra is a continuous function on the maximal spectrum. And we get a map from A to the algebra of continuous functions on the maximal spectrum. This map is also called the Gelfand transform of the algebra. So by definition, the Gelfand transform of A of the algebra is a map denoted by gamma from A to the algebra of continuous functions on the maximal spectrum. And this map takes each element little a to the function little a hat. The following our lecture result describes some fundamental properties of the Gelfand transform. First of all, gamma is a unital homomorphism. Gamma is a unital algebra homomorphism. Second, gamma is continuous, and the norm of gamma equals 1. Property 3, if we take an element little a in our algebra, then the norm of its Gelfand transform, the supremum norm of a hat, equals the spectral radius of A. Equals the spectral radius of A. Part 4, for each element in our algebra, the spectrum of A equals the range of its Gelfand transform. So we have the following equality. And finally, property 5, the kernel, or the Gelfand transform, is equal to the intersection of all maximal ideals intersection of all maximal ideals. And this is the same as the intersection of all kernels of all characters. And this is the same as the set of all quasi-nilpotent elements. So let's recall that an element of a unital Banach algebra is quasi-nilpotent if its spectrum is 0, or equivalently if its spectral radius is 0. And equivalent to this means that the norms of the powers of this element go to 0 faster than any exponential. So a typical example of a quasi-nilpotent element is an element A such that the norm of A to the power n behaves like 1 over n factorial. So it goes to 0 very quickly. Well, the first part is more or less clear from the definition. It's a unital homomorphism. It follows from the definition of little a hat. Now it will be more convenient to start with part 4 and to show that this equality holds. Well, why is it so? We observe that the right-hand side of this formula, is nothing but the spectrum of a hat in the algebra of continuous functions. So formula 4 means that the Gelfand transform gamma preserves the spectrum. So the spectrum of A equals the spectrum of A hat. But we know that unital homomorphism preserves the spectrum if and only if it takes non-invertibles to non-invertibles. So to prove 4, it now suffices to show that gamma takes non-invertibles to non-invertibles. Okay, so let's take a non-invertible element in A. A is a non-invertible element of A. And let's recall the invertibility criterion, which was discussed some time ago. So the criterion was that an element of a unital, of a commutative unital bound algebra is not invertible, even if the characters don't vanish on this element. So it is not invertible, and our criterion implies that there is a character, chi, which vanishes at A. In other words, this means that the Gelfand transform A hat vanishes at chi. But this means the existence of such a point means that A hat is not invertible. A hat is not invertible in the algebra of continuous functions. And so this proves part 4. Okay, now let's look at part 3. Part 3 easily follows from part 4 because we have the following. The spectral radius of A is the supremum of this set, or more exactly the supremum, well, not the supremum of the absolute values from the spectrum. But the spectrum is equal to the range of a hat, and the supremum of the absolute values of points in this set is nothing but the supremum norm. So 3 follows from 4. Okay, now part 2. Part 2 follows from part 3 because we know that for each element in A, the spectral radius is less than or equal to the norm. So since the norm of A hat is equal to the spectral radius, and the spectral radius is less than or equal to the norm, we conclude that gamma is bounded, and the norm of gamma is less than or equal to 1. But since it is unital, gamma is unital, and the norm of the identity element is 1, this implies that the norm of gamma is actually 1. And finally, part 5. Well, if we look at, let's start with the right-hand side not with the right-hand side, but with this part of the formula. So we start with the intersection of all maximal ideals. The intersection of all maximal ideals of our algebra. So by means of the bijections between the maximal spectrum and the character space, we see that this is the same as the intersection of the kernels of all characters, of all non-zero characters of A. Okay, but by the definition of the Gelfand transform, this intersection is precisely the kernel of the Gelfand transform. This follows from the definition of the Gelfand transform. And finally, we apply part 3, and we see that the kernel of the Gelfand transform consists precisely of those elements A for which this is 0. That is, the spectral radius is 0. But the spectral radius is 0 means exactly that our element is quasi-nilpotent. So by part 3, we conclude that this is nothing but the set of all quasi-nilpotents. And this completes the proof. Well, in conclusion, I just want to say that in a general case, that is for arbitrary commutative unital algebras, not necessarily Banach algebras, but for an arbitrary commutative unital algebra, and in fact for each commutative ring, this set, the intersection of all maximal ideals, has a special name. It is the so-called Jacobson radical. So if A is a commutative unital algebra, then the Jacobson radical of A is the intersection, it will be denoted by J of A. This is the intersection of all maximal ideals. And if this is 0, then we say that A is Jacobson semi-simple. A is Jacobson semi-simple. If this is 0. So if you know some basic commutative algebra, then you may compare this with nil radical, which consists of all nilpotent elements, and which is equivalent to the intersection of all prime ideals. So the nil radical is generally smaller than the Jacobson radical. And the two respective notions of semi-simplicity are not equivalent for arbitrary algebras. So roughly, if we now come back again to the definition of the Griffin transform, we see that in some sense, if we start with the semi-simple, Jacobson semi-simple, commutative unital Banach algebra, then this algebra modulo some details becomes a subalgebra of the algebra of continuous functions. The details are important because the details, one of the important details is the norm. So the norm on A is not necessarily the supremum norm. It can be strictly stronger. But anyway, you have an injection of A into the algebra of continuous functions on the maximal spectrum, provided that A is Jacobson semi-simple. But on the other hand, there are some examples of commutative unital Banach algebras which are not Jacobson semi-simple, and for which the Griffin transform forgets some important information about the algebra. So in the next lecture, we consider some concrete examples of the Griffin transform, and then we move from arbitrary Banach algebras to an important subclass which consists of C-star algebras, and we will prove a fundamental theorem due to Griffin and Nymark, which states that if we start with a commutative unital C-star algebra, then the Griffin transform will be an isomorphism. Okay, thank you. That's all for today.